Okay, so in the last video we saw how delta G and Keq are related, and now we're going to see that both of them are dependent on temperature. There's a temperature component to both of those in the equation. So we're going to kind of do what is typical for physics. We're going to take two equations and smash them together. So the first equation we learned for delta G is that it's delta H minus T delta S. If this is at standard conditions, then these are at standard conditions. Okay. The second equation only works at standard conditions, which is why we have to have this first one at standard conditions. So delta G is equal to this, and delta G is equal to this, so we're just going to set these two things equal to each other. Okay, so delta H minus T delta S is this part, and that's equal to delta G, and this bottom part is also equal to delta G, so we're just going to set that as the other side. Okay. Well, we can kind of rearrange things to solve for natural log of Keq. Basically, we would divide everything by minus RT. Okay, and I'm going to save us some of the steps in algebra and just kind of work towards the answer here. Okay, this comes out to negative delta H divided by RT plus delta S divided by R. Because the temperature canceled out, we can basically assume this is a constant. Okay. And in terms of relating Keq to temperature, we can plot natural log of Keq versus 1 over temperature, because temperature's on the bottom here. I'm not actually going to worry about making the graph here, but we're going to kind of look at the consequences, and hopefully it looks somewhat familiar, actually. It turns out that if you have two different Keq values, two different equilibrium constants, and two different temperatures, there is a relationship between these, okay? I'm just going to call this K instead of Keq1 and Keq2. And this is equal to delta H divided by R 1 over T1 minus 1 over T2. This is known as the Vant-Hoff equation. I guess I didn't tell you the name the first time we saw this, but we actually saw this about 4 or 5 chapters ago, maybe even more, like probably 6 chapters ago. We've actually seen this on quizzes and exams. This isn't even new material, okay? And your equilibrium constant, if you have a sublimation or a vaporization process, so for vaporization or sublimation, or in other words, you're going from a liquid to a gas, liquid to a gas or a solid to a gas, so basically a phase change. If you have a balanced equation, so for example, if you have compound A going from a liquid to a gas, the equilibrium constant for this would be, this is a liquid, you can ignore it, is basically just equal to the pressure of A, just the product. So in other words, we can actually substitute in pressures for equilibriums, okay? And we get this equation. So if this is vaporization, and guess what? We've seen that equation too. So we're just kind of seeing these equations from another perspective, but really there's nothing new here, but it is technically all related to these, like it's kind of derived from these equations. Okay, and because delta S doesn't change with temperature because it just factors out like that, we can actually derive these equations that we've kind of actually seen before. So I know it's been a hot minute since we've seen these, so let's do an example just so you have one in your notes. All right, so if the delta H of vaporization equals 15.6 kilojoules per mole for a liquid, and the vapor pressure is 0.0162 atmospheres at 298 Kelvin, what will the vapor pressure be at 350 Kelvin? Well, for vaporization, we have this equation. So the equation is natural log of P2 over P1 equals delta H of vaporization divided by R, which is a constant, times 1 over T1 minus 1 over T2. Well, we have delta H, R is a constant. We have some pressure and temperatures, let's call that P1 and T1. We have a T2, and we want to know what is P2. Okay, so let's rearrange this equation to solve for P2. Since we need to solve for one of these two things, we're going to have to get rid of the natural log first, which means all of this is now an exponent. And then we multiply P1 to the other side. I guess I'll put all that in some sort of bracket or something. Okay, so rewrite that so it looks more like an exponent. Okay. We have all of these numbers, so we just plug them in. Okay, so I'm gonna write all the way over here just to give a space, but P1 is 0.0162 atmospheres. E is a button on your calculator as far as you're concerned. R is 8.314 joules per mole Kelvin. And since this is in joules, we're gonna need this in joules. So this is 15,600 joules per mole. And this is 1 over 298 Kelvin minus 1 over 350 Kelvin. Typing all this in can be a little difficult, so go slow, make sure you're careful and diligent about everything. I'm going to do the exponent stuff first. So 15,600 divided by 8.314. Going to hit equals, whatever that number is, I don't even actually care right now, times 1 divided by 298 minus 1 divided by 350. Great, so we got all of this. That is the exponent of E, so I'm going to do E to the answer. And I got 2.54, and then times 0.0162. So it comes out to 0.0413. For what it's worth, we've technically seen this equation before, but since it came up again in this chapter, I figure I should reiterate it and get extra practice. So that is officially the end of chapter 18. It's actually a really short chapter. So thank you guys.